Accuracy and precision are the same thing, right? Absolutely not. Absolutely not. They are two different words, and so we need to separate them. Accuracy refers to the closeness of a measurement to the true value or accepted value. Same thing. Or I might even call it the literature value. Now, precision refers to the agreement among the numerical values of a set of measurements. So if you see the target that's here on the left, if it's hitting the bullseye, it's accurate. And if the X's are close together, then it's precise. Here, the X's are close together, so it's precise, but it's not on the target, so it is not accurate. And for the third one, it has high accuracy, but also low, but very low precision. Since the precision is so low, it's affecting the accuracy of the target. So they're not actually hitting the target very well. And then for the last one, it's just all over the place and is a bogus measurement. So something's going on with that experiment. So for our examples, I want you to comment on the accuracy and precision of the following. If you look at number one, which group was the most precise? You have four groups, A, B, C, and D. And then each group took four readings. So I want you to look at their accuracy and precision. Welcome back. So for D, D was the one that is the most precise because all their measurements are the closest together and they are the best. Now, you see that group A was all over the place. And then group B had two students that were high, two students that were low. And then group C had an outlier here, but group D had everybody pretty much the same. Now there is no true value, so we don't know the accuracy. We cannot comment on the accuracy for number one, okay? We can only comment on the precision. But for number two, we can comment on the accuracy because we have this true value, okay? So a student measured the mass of a beaker 3 times with the following results. Trial 1 equals 32.55 grams. Trial 2 is 32.56 grams. Trial 3 is 32.55 grams. The actual mass is 32.96 grams. So we can tell that they are precise because the measurements are quite close together and they're pretty tight. Now they are not accurate though, because the average of the trials is a little far off. So I'll go ahead and write down the average for you. And the average is going to be 32.55. Well, this number, my average, is far away from that one. Okay. Now, instead of doing number 3, let's go ahead and take a look at it's a real life example. On the left, you have a beaker, and on the right, you have a graduated cylinder. Hey, we have done this before. I just want to talk about this, a graduated cylinder. So when y'all did the lab, I asked you which measurement did you feel more confident in, and I had a lot of students pick this one as the one they felt more confident in. I don't know why, because this one is much more precise. Okay, the graduated cylinder is so much more precise than the beaker. The beaker is not used for measuring, and you can even read on the label, it says approximate volume. You should not be confident in that volume on the beaker. You should be much more confident in the graduated cylinder, okay? So if anybody asks you again, which one are you more confident in, you should always be looking at either a graduated cylinder or a burette. I don't want to ever see another student measuring from a beaker, okay? So just wanted to pass that along to y'all. Anyways, so when I look at the three basketball players, and they were shooting some shots in the basket. LeBron James hit 33 on the top of the backboard, 33 off the back of the rim, and 33 air balls. Well, LeBron James is not accurate, and he is also not precise. Okay? Because none of the measurements were together, and none of them were in the basket. Now, Michael Jordan hit some off the back of the rim, so he was not accurate, but but very precise. Now, Mr. Russell hits all 9 of his free throws, so Mr. Russell is precise, but also accurate. Okay? That is probably the absolute opposite of what would really happen. So that is it for accuracy and precision. We're going to move on to scientific notation. Scientific notation is a way to express very large or very small numbers in a much more convenient fashion. Scientific notation can also be used to express a number to the proper number of significant figures, which you learned last week. So scientific notation is there's just no way we can get around it. We're going to use numbers like 6.02 times 10 to the 23rd because we're talking about atoms, and atoms are super tiny. So when you group them all together, you get a huge, huge number. And then we're also going to use numbers like this, 6.626 times 10 to the minus 34. Oh, the minus 34. And that is a super tiny number, okay? Again, because we're looking at the atomic realm. I sound like I'm talking from Ant-Man. But a scientific notation is talking about a coefficient and an exponent, all right? So coefficients is the coefficient must be a digit between 1 and 10, okay? It cannot be 10, and it cannot be, I guess it could be 1. It could be 1, but it cannot be 10. It cannot, so it always starts with a significant digit, so that's why it's easy, it's convenient for sig figs as well. So to convert the following to scientific notation, the way we are going to do this is we take our pencil, we put it on the decimal place, and we move it however many places to the left. Now here, I moved it to the left. So I'm going to write 2.19 times 10 to the 1. Okay? Now the reason why I moved it over one place to the left is because I'm moving it to after the first non-zero number. I want to have one non-zero number on the left side and then a decimal place. You will always get that. Now for part B, I'm going to put my pencil on the decimal and I'm going to move it over 1, 2, 3. So I moved 3 places. So that's going to be 3.32 times 10 to the minus 3. Now, if you hadn't seen, if you move the decimal place to the left, then your exponent is positive. If you move the decimal place to the right, then your exponent is going to be negative. Now for 3.21 times 10 to the 2. 1.19 times 10 to the minus 1. 1.492 times 10 to the third. Okay? Now, you may be asking yourself, Mr. Russell, why can't I just write these numbers? Well, normally you would be able to. But for now, I just want you to focus on scientific notation. For F, 2.713 times 10 to the minus 1. Notice how I moved the decimal place one place to the right, so my exponent is -1. For G, imagine a decimal place. Move it 1, 2, 3, 4, 5. 5 places. So it's going to be 3.14159 times 10 to the 5. We moved it 5 places. You must include all the significant digits, all the digits that are still there. Your answer should include the same number of sig figs as the one before it. For example, for A, there were 3 sig figs here and 3 sig figs here. For part B, there were 3 sig figs in my original answer, so I need to have 3 sig figs in my scientific notation. And then for H, 6.022 times 10 times 10 to the third, and this is 1.2011 times 10 to the minus 1. All right. Now let's do the opposite way. For A, what we'll do is we'll take this decimal place, and it's 10 to the third, so we're actually going to move the decimal place. We're going to switch those directions. Remember those directions I said over here? Moving it left if it was a positive and moving it right if it's a negative. Well, this time we're going to switch them. So this is 10 to the third, so it's a positive exponent, which means the number, this value right here, is going to be a large number. It's going to be a number greater than 1. Okay? So the answer is going to be 3825. What I did is I moved the decimal place 1, 2, 3 places to the right. Okay, that's backwards than the section you did before. And this is 6300. Okay. And then for this one, you're going to move the decimal place 2 places. So that's the decimal. So it's going to be 0.023. I still have to do this way. For 4.44 times 10 to the minus 6, I'm going to take the decimal. I'm going to loop it once, twice, 3, 4, 5, 6. That's my new decimal place. Okay. And so that's going to be a 0, and I'll write in 0, 0, 0, 0, 0. Okay. So my answer should have 5 zeros. 1, 2, 3, 4, 5, and then 4, 4, 4. For this one, I've been doing this for years, and I still have to do it this way. Loop 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there's my decimal place, so I fill in the zeros. Okay, so that should be 7, 1, 2, 1, 1, 2, 3, 1, 2, 3. Okay, and then this one should be 0.12. This one should be 180. And then this one should be 0.0. Oops, hold on. I gotta write it out. 1, 2, 3, 4. Okay, 4 places. So 1, 2, 3. And then that leading 0. So 3, 8, 1. That's how you do that. I hope you guys enjoyed scientific notation. You will have to get used to it. You will have to use it this year. There is just no way around it. Hey, have a good day and enjoy.